Welcome to our highlight poster session. In this session we introduce our work, eTraM, Event-Based Traffic Monitoring Dataset. This research was conducted at Arizona State University. Event cameras excel in various applications due to their high temporal resolution and efficient memory usage, yet their potential in static traffic monitoring is underexplored. Introducing eTraM, the first event-based traffic monitoring dataset with 10 hours of data across diverse traffic scenarios and conditions, including 2 million bounding boxes for 8 classes of traffic participants, from vehicles to pedestrians and micro-mobility. Through eTraM we demonstrate the impressive potential of event cameras for traffic monitoring, especially in nighttime and unseen conditions. Current perception systems predominantly use frame cameras that face inherent challenges such as a loss of object features and excessive motion blur, especially in low-light conditions. They also have increased redundancy while requiring a large bandwidth. Detection methods must be fast enough to operate in real time and be insensitive to illumination change in varying weather conditions. In the face of these challenges, we propose a new static event-based traffic monitoring dataset, eTraM. We aim to use event cameras for their high temporal resolution, high dynamic range and resistance to motion blur. Their low light cutoff and invariance to absolute illumination are especially useful at night. These features make event cameras a promising tool for improving traffic monitoring in varying lighting conditions. While most existing event-based datasets are captured from an ego motion perspective, eTraM is unique for being the first dataset designed from a static perspective specifically for traffic monitoring in ITS. Its comprehensive features make eTraM stand out, providing invaluable insights for event-based research and real-world traffic analysis. eTraM consists of 8 distinct classes: pedestrian, car, bicycle, bus, bike, truck, tram and wheelchair. The heat map illustrates the spatial distribution of each class within the frame. eTraM also has data sequences from distinct traffic sites including intersections, roadways and local streets with varying day, nighttime and twilight conditions. eTraM, being a static dataset, has highly sparse distribution due to no extraneous background events as opposed to other ego motion datasets. This allows eTraM to have events lesser by a factor of over 30 compared to the other well-known event-based datasets like DSEC and the 1 megapixel dataset. Its elevated position captures a larger field of view with enhanced visibility of objects of interest due to events existing solely due to dynamic objects. Now we present the results of experiments evaluating eTraM for real-world detection scenarios. We use 3 state-of-the-art detection models. First, we use a conventional frame-based method, YOLO. This method is composed of a series of convolution layers. Another method used is the recurrent event camera detector, RED. Created specifically for event-based data, it includes LSTMs along with multiple convolution blocks. The third state-of-the-art method we use is the recurrent vision transformer, RVT. Inspired by vision transformers, it consists of LSTMs between RVT blocks for temporal aggregation. We establish benchmarks using these models and observe intriguing results. A comparable performance during day and nighttime conditions shows the potential of using event cameras for detection in day as well as nighttime conditions. Architectures with recurrent networks outperform the traditional CNN-based architecture, showcasing the importance of temporal aggregation in event data. Further investigating the comparable performance between day and nighttime conditions from our previous experiment, we evaluate the need of nighttime data for the training process. We train a model on only day data and compare it with a model trained on night data as well. The consistent stronger performance by the second model strongly indicates the importance of nighttime data for effective generalization, thus further demonstrating the strength of eTraM that contains over 800K night data annotations. Since the model only observes the relevant objects and no background events during the training process, we further evaluate how well event-based detectors learn the concept of these objects in our dataset. For this, we compare how the model performs on an intersection it has not seen during training. The comparable performance of the models across both the major categories considered shows its potential to generalize to unseen scenes. This transferability to new scenarios is a key characteristic required for real-world deployment. Event cameras excel in capturing instantaneous changes in the visual scene, making them great tools for motion detection and estimation. We show this through the snapshots of traffic at a stop sign. This property enables precise detection of vehicles coming to a halt, as can be seen in column 3 of the first row, while the vehicle in the second row produces events in every snapshot showing that it violates the stop sign. Another advantage of event cameras lies in its property of registering events with no color and texture information, significantly reducing the probability of gathering sensitive information of individuals as illustrated in the video. In conclusion, we present eTraM, a large-scale, manually annotated event-based dataset for traffic monitoring. Captured with the Prophecy EVK4 HD camera, eTraM offers 10 hours of data across various scenes and conditions, including 2 million bounding boxes of diverse traffic participants. Our results show that event-based models generalize well to nighttime and unseen scenarios, making eTraM a valuable resource for advancing event-based research and intelligent transportation systems. Thank you for your attention. For any questions or further information, please visit our GitHub page or contact us at the provided link.